Hello everybody, this is Farhad and this is going to be our new method of delivery for the labs for Math 366. If you have any questions about the structure of the course or anything else that's changing, feel free to email me at any time and I should get back to you within a day or so. But yeah, let's get into it. Um, so this week we're going to do Lab 9, which focuses on predator-prey problems and basically looks at the interaction between predators and prey and their population, how the populations affect each other. So if you read the discussion given in the lab, it basically describes an Italian biologist who was studying the populations of fish that were caught during the years of World War One around like the Mediterranean area, and the data given in the table is the percentage of Salacians caught, and Salacians are basically predators like sharks and skates and rays, as they say, uh, and these are like the fish that are caught in like the large nets that are used, but they're not actually used for food or anything, so they're kind of unintentionally caught. And so, as you can see from the data, World War One was from 1914 to 1918, and so 1914 was just the beginning. And so the years after that, 1915, 16, 17, 18, and even to 19, percentage of the predators caught in the whole uh, in the nets that were used were increased during World War One. And so the biologist was studying these patterns and tried to make sense of it. Um, the reason that he initially came up with was that during the war there was decreased fishing, and so decreased fishing just increased the population of uh, the predators. But then it would also the problem with that was that it would also increase the population of the prey, and so the percentage of the predators caught shouldn't have increased. And so he was puzzled. So he went to his mathematician friend, um, who ended up making this mathematical model that we see here. Um, with these equations over here. And the equations are arrived at through pretty simple reasoning. If we assume that x is the population of the prey and y is the population of the predators, um, we say that the population of the prey will be directly proportional to the population. The rate of change of the population of the prey will be directly proportional to the population of the prey itself, because the larger the population, the more they'll be able to reproduce. And that combining that with the fact that they don't have to compete too much, uh, they don't have to compete with each other for food. So this the larger the population, the faster the population of the prey will grow. So that's why we have this positive ax term that's over there, and the negative bxy term uh, comes from the fact that xy is supposed to be proportional to the number of encounters between the predator and prey. So like if x or y increase, the number of encounters between them will increase. So we can estimate the number of encounters between the two using the product. And so the larger number of encounters there are between the predator and the prey, um, the more prey will be eaten, and therefore the population will decrease. And so we have this negative term over here. And a and b are just proportionality constants. With the very similar logic, we can come up with an equation for the population of the predators, which, but over here, the one difference is that it's going to be negatively proportional to its own population. And the reason for that is that the predator is going to have to compete with other predators for its food source. So, like the larger number of predators there are, um, the harder it will be to get food. And so the population decreases with an increase in population, but the population will increase with the number of encounters. And so that's the XY is just the number of encounters. And so it's a very similar situation to the previous one, but just that the more encounters there are, the more the predator gets to eat because they see more prey. And so that's why we have the second equation over here. So this is the model that we're going to work with throughout the lab. All right, so let's get into the first question. So the lab asks us to assume certain values for the proportionality constants. Um, and so if you take those values, we get this system over here. Um, and the first question just asks you to find the equilibrium points for the solution for this system of equations. And the equilibrium points are just when you set x prime and y prime to 0. And so you set these equations over here, the right hand side is to 0. And you should find two different equilibrium points. One of them will be the trivial one. We can see that if x is 0 over here, x prime will be 0, if y is 0, y prime will be 0. But this is another equilibrium point that you'll have to find. And so this question requires you to only find the next equilibrium point. The second question asks you to graph this in p-plane, um, and then asks you to note something about what you see in p-plane. So if you plot it in p-plane, you should get a graph that looks something like that. And you'll notice that what we're interested in is the first quadrant. And in the first quadrant, you'll notice that there are closed loops over here. So the question asks you what the significance of these closed loops is. And what it's asking is, this word physical is really important, um, because it's not just saying what is happening, what does it mean mathematically. It means what does this mean about the populations? How are they changing? How are the populations changing over time? Um, and so that's what you really have to address, uh, based on what these closed loops mean. What does it mean about how the populations are changing over time? The next question asks you, it gives you the system of equations. You write it as a single differential equation, and you need to explain how you get this differential equation, just combining systems of it, as we've done many times before. You just, yeah, you know how to do this. You combine the two systems, the equations that we have in the system of equations from the previous questions. And then you plot this, you get this equation over here, you plot it in D field. Uh, and you'll notice that the plots, although they should be what we got from the previous question, you'll notice that they're like kind of chopped up in half, where only the top half plots, and then you click somewhere else, and then only the bottom half will plot. And that's not what that's not what's actually happening. But there's a problem with plotting this on D field, or rather just a limitation of D field, or converting this to a single equation. And so you need to describe what that limitation is. And the hint for this is to look carefully at this equation over here and uh, what happens to the denominator at different values, and what that means. What will D field do when something special happens to the denominator? Question 4 asks you to solve the differential equation from the previous question, and it's a separable equation, so you just put all the terms of y on one side, all the terms of x on one side, and you integrate both sides, and you'll get an implicit solution that will look like this. So you need to show all your steps for this question, and this should be your answer over here. That's pretty much it. Again, all the steps need to be shown for you to get all the points. So question 5 is probably one of the longest questions on the lab. What we start by doing is assuming that c equals half, and so that's just the same as choosing an integration constant, and so it's the same as getting an initial condition and calculating c. So we let c equals half, and then we end up with this equation over here on the right. And what part 5 a is asking you to do is plug in x equals 1 and then approximate what y would be when x equals 1. So when the population of the prey is 1, what will the population of the predators be, given some initial conditions such that c equals half. And to do this, you need to plug in x equals 1 on the left-hand side of the equation over here. So for x, you put in 1 and you evaluate what that is, and then the lab gives you that it is equal to 0.642. And so you need to figure out what value of y would make the right-hand side that's being highlighted over here, what value of y would make the right-hand side equal to 0.642. And to figure out the value of y, the easiest way to do it is to just plot this function of y. The lab asks you to use fplot in MATLAB, but if you're having trouble using MATLAB, I put the instructions up on how to use MATLAB in the announcements section of Blackboard. But if you're having trouble using MATLAB, you can just use any other plotting software that you can find on Google, for example, like Desmos or something like that. But you can just plot this function on the right-hand side and see when it equals to this 0.642, and that'll give you the value of y, which satisfies this equation when x equals 1. 5b asks you to do the exact same thing, but for all these different values of x, from 2 till 10. And so you just, for each one, you just plug in, for example, 2, you plug in 2 into this, the left-hand side of the equation. You figure out what it equals to, and then you look at the graph for the right-hand side of the equation and figure out what value of y will make that function equal to the computed value of the left-hand side. And so it requires many steps, and I think the easiest way to do this is just make a table with all the x values from 1 to 10, and then the calculated left-hand side, and then the y values. And you'll see that for most x values that you use, you'll find two different y values that for which this function equals to like the required value. And the question also asks you to explain why you typically have two such y values. And you'll be able to explain this once you see what the plot of this function over here is. Once you see what the plot looks like, it'll make more sense of like why they're typically two different y values which satisfy the equation for any given x. And then the next part of the question asks you to approximate the largest value of x for which there's a corresponding y. And again, this will make more sense once you actually plot the function on the right and you see what it looks like. But you'll see that after a certain point, after the function value doesn't go above a certain point, that is, it has a maximum. And so for any values of x that go beyond that maximum, there won't be a corresponding y value. And so given that you have a maximum function value, you need to try to figure out what x value would be the largest such that it's still within the maximum attainable value of the function on the right-hand side. And the lab suggests that plotting this function on the left, the function of x, will be useful for this to like find the corresponding x value for which you can get the maximum maximum function value such that there is still a corresponding y. Again, this is tricky. If you're having troubles with it, just post something on the discussion board or send me an email. But hopefully that made sense. 5c is similar to the previous question, but this time instead of finding the largest value of x, you need to find the smallest value of x such that there's a corresponding y. And again, if you plot the function on the right-hand side, on the left-hand side, sorry, the function of x, this function over here, you'll be able to see that you can also find the smallest value for which there is still a corresponding y that satisfies the equation. It also asks to explain why there's only one corresponding y value. And this again will make sense once you see the two graphs and see the way they're shaped. And you'll be able to explain, again, based on the graphs, explain why there's only one y value for that given that chosen value of x that you find the smallest x. So one way to write the equation that we had from the previous slide is to let those functions, we had two functions, let them just be equal to f of x and g of y. And then we can relate the two, like if we don't assume c equals half, we can relate the two using this equation over here, g of y equals c divided by f of x. And again, this is just the same equation as we had before, but we're just simplifying it by using f and g as functions. And so the first question that you have to answer, the first part of the question is that if the orbits begin in the first quadrant, then c is greater than 0. Why? And again, just look at this equation and try to figure out what the signs are, what the values of g and f would be in the first quadrant, and what this would imply about c. And that's pretty straightforward. The next part of the question asks you to plot g of y for y between 0 and 6. You can do this using fplot, or again, you can use another graphing software, but I recommend fplot just so that you get used to it. Um, and it asks you to explain that if there is a positive value of y, there will always be two of them. And this will be clear again once you actually see the plot. It's very similar reasons to some of the reasons you gave uh, in the previous question. And also you can relate it to the fact that the orbits initially were closed orbits. So those are two hints. And then explain why f of x goes to 0 as x goes to infinity. Here you don't have to formally show a limit, but you can just kind of give an explanation based on what you know about the two functions, or the forms of the functions in f of x. Like how does the exponential grow? How does e to the like compare x to the power of 0.75 and e to the power of 0.25x? Which one will grow faster, and what does that imply about f of x? Um, and so then you use these facts together, um, namely the two positive values of y and the limit of f. You can use them together to show that for sufficiently large and small values of x, there will be no values of y for which the equation holds. And again, the way to do this is again go back to this equation over here, which relates g of y to f of x. And so for sufficiently large or small values of x, what happens to this, and then what happens to this equation over here? Then what does that tell us about g of y? And what happens to g of y? What does that tell us about the actual values of y in the equation? And so that's how you relate it back to show that there will actually be no values of y for which the equation holds for large values of x. And since for large values of x there will be no corresponding values of y, and if there is a positive value of y, there will be two of them. You can kind of infer that the orbits will be closed loops because it's now going infinitely to the left or to the right, because we know that there is no y for such large or small values of x, and that for each value of x for which there is a y, there will be two of them. And so you can infer from these two just by thinking graphically that all the orbits will be closed loops. Question 7 is a rather quick one. It just asks you to plot x and y as a function of time for the different initial conditions. And we've done this before. Again, you need to go to p-plane, plot the orbits first, and then go to the options above and then plot y against t and x against t. And you should see some sort of sinusoidal kind of wave. And so they are. You can answer the question based on what you see. Are they periodic, and does the period depend on the initial condition? Uh, and to answer the question of does the period depend on the initial condition, you just maybe enter two different initial conditions to get two different orbits, or just click on two different places. But make sure you click in the first quadrant, because those are the only realistic ones. And then you can plot those against time, x and y against time, and see if they are periodic and if the period changes when the initial condition changes. So from the previous question, we see that the populations are in fact periodic. And so we can find an average value of the populations for each given period using the formulas described over here at the top of the page. And so what this is basically the capital T is the period, so the actual time it takes for the population to go around a whole circle, if you may, and come back to the population that it was at the beginning. And if we just integrate over the period, the population, and divide that by the period itself, we can get some notion of an average value for the population of the prey and the population of the predators. But the problem over here is that we don't actually know x of t and y of t. We just have differential equations that describe them. But there's a trick that we can use to find these average values in a way that we don't have to evaluate these integrals. And how you do that is the lab shows us how to do it for x bar, and we need to figure it out for y bar. So to find the average value of x bar, what you do is you start with the differential equation for y. So you have y prime equals, and you have that differential equation from the initial system. And what you do is you just integrate both sides, bring the one y to the left hand side, and then you integrate both sides. And on the left hand side, you'll just get the natural logarithm, and you divide both sides by capital T again, the period, and then integrate. On the left hand side, as you seen here, you'll get the natural logarithm, and you apply the limits. And on the right hand side, for this negative 0.5 over here, you integrate it over t, you'll get just negative 0.5 times small t, and you apply the limits over here, 0 and capital T. Uh, and obviously when you have 0 over here, it's just going to be negative 0.75 times 0, which is be 0. And then for the upper limit, you'll have negative 0.75 times capital T, but then you're also dividing it by this factor over here. And so that's why you just get negative 0.75 here. And for the second term, you just leave the integral. You don't do it yet. And what you notice is that if you take out the 0.25 over here, if you take that out, since it's a constant, the term that you have remaining is exactly equal to the definition of x bar given up here. Um, and so we can just substitute that integral for x bar as done in the next step over here. And then it's really simple to algebraically solve for x bar, and we find it to be 3. And so what you have to do for this question is find out where y bar is. And so you do it in a really similar way. Just start with the differential equation for x and then follow the exact same procedure, and then you'll be able to find out what y bar is. And then in relation to the orbits on your graph, so you'll have x bar and y bar, where does that point lie on the graph in relation to the orbits that you've plotted? Could you answer that question too? Question 9 is the last and final question, and we finally come to fishing. And our original question, if you remember, we started with what are the effects of fishing, because we wanted to know why we observed certain changes during World War One. And so our new system of equations uh, is given by this thing where fishing we know will decrease both the population of the predators and of the prey. And the rate of decrease will be proportional to the population itself, because if there are a large number of prey, you're going to be able to fish a lot of them, and so then the population will decrease at a larger rate, and the same for the predators. So we just assume that they both have the same proportionality constant, because fishing would be unbiased towards predators and prey. Uh, we assume, and so we take alpha to be 0.05, and so you plot some new orbits of this system, and the question asks you if they're still closed orbits, and so you just say yes, they are closed orbits, or no, they're not closed orbits. And then it says compute the average populations as in question 8. So exactly as is in the previous question, you use the same trick as before with these new differential equations. So you'll have this new factor of 0.05 here. So you need to calculate both x bar and y bar. And you can use the exact same trick as before, and you'll get different averages, and then you have to compare the new averages you get with the averages from the previous question when there was no fishing present. And finally, we have an answer of what will happen to the average populations of the predators and average populations of the prey if you introduce fishing. And so you need to say, does this increase and decrease of the average populations agree with the data that we saw on the table at the beginning of the lab? We saw that the percentage of the predators increased, and so is that in accordance with what we found with these averages, or do our average values go against it? And so just calculate the averages and give a conclusion based on what you see and compare it to the data. So that's it for this lab. I'm sorry for making it so long. I'll try cutting it down for the next few videos. If you have any feedback on the videos, please send me an email and I'll try incorporating it and make these more concise so that it's easier to consume. If you have questions about the lab itself, please use the discussion forums on Blackboard so that everyone else can benefit from your questions too. Or you could even just email me if you have questions about grading or about the course structure in general. Please remember to check the grading rubrics because that's how I'll be grading you, so you can see exactly what you'll be getting points for, and make sure you submit the plots for the right questions and all of that stuff. Um, and again, if you have questions, just feel free to contact me at any time. And I hope you all stay safe during these tough times. Goodbye.